Howdy! In this video we're going to look at pendulums in simple harmonic motion. And while pendulum motion is not true harmonic motion, it is very approximately harmonic motion for small angles of theta, where we start the pendulum at small angles of displacement. Then it's very, very close to simple harmonic motion. And in this derivation, we're going to use the small angle approximation. And you'll see why the small angle approximation is a good one, and why it's only simple harmonic motion when we use small angles of theta. So we have to remember that when we looked at springs, we looked at the fact that the opposite of the position is going to be proportional to the acceleration, which is the second derivative of the position. And this is the requirement for something to be in simple harmonic motion. So specifically, we're going to be looking for some constant times the position to be equal to the second derivative of the position. And when we look at pendulums, we are, instead of looking at forces, we're going to start to look at torques. So here we've got a pendulum, and it is displaced by an angle of theta from the horizontal. And it has a mass m. And it's got a force of gravity, the weight going down on it. So we've got mg going down this way. And we are not going to look at linear forces. We're going to look at torques. So we know that we have a vertical component, or let's call it the parallel component of mg, and we have this horizontal component, a perpendicular component of mg. And it's that perpendicular component that we care about. So let's draw that picture in more detail, and we're going to use it on the next slide. Alright, so here's our picture drawn a little bit bigger, a little bit better. And we see that the components of the weight force are the mg parallel, which is going parallel to L, and mg perpendicular, which is going perpendicular to L. And it's the mg perpendicular that's responsible for the torque that is going to cause the angular acceleration on this ball. So let's start there. We're going to say that the sum of the torques acting is going to equal the I for the ball times its alpha. The only torque that we really care about in causing the acceleration is going to be mg perpendicular. So that's going to be the magnitude of the force. And first we need to take a look at the fact that this angle in here is theta as well, identical to, I forgot to draw it, this angle theta right here. Those are both the same angle theta. So then mg perpendicular, we're looking at the sine. So we have the magnitude of the force, which is going to be mg times the sine of theta, times the distance it is away from the axis, and the axis of rotation is right here where our pendulum's attached to the ceiling. So that's going to be times L. And that's going to equal I for a point mass is going to be m times the distance from the axis squared, times alpha. And let's go ahead and say that alpha is the second derivative of the position, the angular position of the pendulum. So from here we can see that there's some simplification that happens. The mass cancels from both sides. We have one L canceling from both sides. So rewriting this, we have g sine theta is equal to L times the second derivative of the angular position. Dividing both sides by L, we have g over L sine theta is equal to d squared theta dt squared. And we're almost at the place where the position is going to be proportional to the second derivative. But upon reflection, I've forgotten one very important thing. The way I've drawn this is the torque from this guy, mg perpendicular. If we use the right-hand rule, that causes a rotation that is opposite the direction of the acceleration. So there should be a negative out here because this torque was negative. So negative, negative. So remember, our requirement for simple harmonic motion is that the second derivative of the position is proportional to the opposite of the position. And we see that we've almost got that here. We've got the second derivative of position, and it's proportional to the opposite, but it's not proportional to the opposite of the position. It's proportional to the opposite of the sine of the position. This is where we're going to use the small angle approximation. And let me show you why it works. Here is going to be hopefully a graph there it is, a graph of y equals x and y equals sine of x. So think of it as theta and sine of theta. And the curve is obviously the sine graph. The linear graph is the graph of theta. So we can see that for very small, well, not very, but for small values of theta, sine theta and theta are really close to the same. We have to go all the way up here to where x, remember x is theta, theta is equal to 0.5 radians for there to be any appreciable difference. How big is the difference here? Well, sine is 0.509 and theta is just 0.53. So we have 3/100ths of a difference, less than 3/100ths of a difference here in the two. So for small thetas, and by here we're looking at half a radian or less, so from displacement anywhere to 0 to 30 degrees, then we can approximate sine of theta as theta because they're very close for smaller angles of theta. So going back, we can make that approximation. For small, I need the pen here, for small thetas, sine of theta is approximately equal to theta. Anything less than 30 degrees, it's a really, really good approximation. And usually with pendulums, we definitely don't have initial displacements of more than 30 degrees all that often. All right, so let's replace sine of theta with theta. So we have negative g over L. Theta is equal to the second derivative of theta with respect to time. That satisfies our condition. Theta is the position, and d squared theta is the angular acceleration. So when we had that for springs, we said then that the omega, which is the angular frequency, remember, this is not the angular velocity, but the angular frequency, is going to be equal to the square root of the opposite of whatever that constant in front was. All right, so going back, and we look at our condition, this constant right here is the one in front of the position. So putting that into our equation, we've got omega for simple harmonic motion is equal to the square root of the opposite of g over L. So omega then, the opposite of the opposite, which gives us a positive. So omega then is equal to root g over L for a pendulum. And this makes sense. If we increase the length of the pendulum, we are going to decrease the frequency of its oscillation. If we increase g, the acceleration due to gravity, if we go and do this on Jupiter, then we are going to get a bigger angular frequency. Okay, so we can plug that in to our other harmonic motion equations, and we can come up with equations for the position, and these would be the x position and the y position with respect to time. But in general, we're really just looking at how the period and the frequency of oscillation depend on g and L for the pendulum. So if omega for the pendulum is square root of g over L, and again, I want to be very clear that omega is not the angular velocity, because the angular velocity of the pendulum is changing over time. It's going fastest at the bottom, and it's 0 at the top. This omega, the angular frequency, is constant. All right, so be very careful, not the angular velocity in this case. We use the same symbol, but they are not equivalent, not by a long shot here. So we've got our standard relationships between the frequency and the angular frequency. Omega over 2 pi is equal to f, and we have 2 pi over omega is equal to the period. So then the frequency becomes 1 over 2 pi times the square root of g over L. And down here, the period is going to be 2 pi times the inverse of that, square root of L over g. Notice that the period and the frequency do not depend on the mass of the pendulum, and we knew that from before when we looked at conservation of energy. The potential energy at the amplitude is going to equal the kinetic energy at the bottom. Masses cancel out. The mass of the pendulum doesn't matter. Just the length of the string and the acceleration due to gravity. And we're going to apply those to solve problems in pendulum motion. All right? See you next time.